Roberto. Can you hear me? Yeah. I'd like also to thank in general the organizers for having invited me here. So I'm going to give a talk about differential privacy and application to location privacy. This is differential privacy is an approach to privacy protection that has become rather popular in the last years. Here is the plan of the talk. I will start by a general introduction to the problem of privacy, and I will speak a bit about the most common approaches that have been used in the past, in particular anonymization, which is rather naive yet very, very spread. And then I will show some particular example on statistical databases illustrating why it's so difficult to protect privacy. And this will bring directly to the approach of differential privacy. Then I will speak about the utility and, well, the trade-off between utility and privacy. And finally, I will show some extension of differential privacy and an adaptation of this extension to location privacy. Sorry, I have a sore throat. So, well, about the motivation, well, I think I don't need to convince you why privacy has become an issue. In fact, in the modern society, we tend to use more and more electronic devices, which cause the fact that we leave digital traces about every activity we do. And some examples are, for instance, the IP address, which leaks information about the location where I am, the history of requests that leaks information about my interests, the activity in social networks, which leaks a lot of information about your political opinions, your hobbies, your religious beliefs, and so on. And even in your own home, you're not safe, because with the new devices like smart meters, they can leak information about what kind of activities you're about to do, you're doing. And the risk, of course, is that malicious people or malicious entities can collect these digital traces for malicious purposes, or anyway for purposes which you don't approve. For instance, they can send spam, they can use that for profiling, they can do identity theft, they can use it against you, discriminating on the basis of your political ideas, for instance, and so on. So, anonymity, this is, as I said, is the most popular, is the most used approach to privacy protection. Essentially, it consists of removing your identity from the data that are collected by the organization, and practically all the big organizations use anonymity nowadays, essentially because they are obliged to implement some form of privacy protection. And they defend themselves when they are attacked by saying, well, our data are completely anonymized. However, it has been shown in the last decade that anonymization is not at all a solution. There have been a lot of attacks, so-called de-anonymization attacks, that have shown that the anonymity technique is quite vulnerable. The problem in general is that even if you remove the identity from the record, it's always possible to retrieve the identity from other information that are called in a technical sense quasi-identifiers. Okay, so we can take care, of course, of these quasi-identifiers, and in fact there are more sophisticated techniques called, for instance, K-anonymity or L-anonymity. However, even if you take care of the quasi-identifiers, there are more sophisticated attacks based on composition, so they're called the composition attacks, that even if the database has been sanitized by using, for instance, k-anonymity, still you can de-anonymize it. And I'd like to give you some examples of famous attacks in the literature. Perhaps the most, one of the first very famous one is the one of Sweeney. What she did was to show that you can take two databases, so you can take a database that has been sanitized by anonymization, so that would be the database 1. It works. And okay, so this database 1 contains sensitive information but has been anonymized. So there are records containing, for instance, medical information, but there is no name associated to this medical information. However, there are other information, and if you combine this other information with the information contained in a public database, which would be the database 2, which contains, besides this other, which links this other information to the names, then you can de-anonymize the record. So let me be more precise about this. Suppose that the first database is in fact a database of medical data, and it has been anonymized, so it contains information like ethnicity, visit date, the kind of disease, the medication, and so on, but also contains information like the zip code, the birth date, and the sex. And now you take a second database, which is public, like the voter list in the USA. This is public information. And suppose that, well, don't suppose, it is the case that the second database contains the information like zip code, the birth date, and sex, and associated to that the name, the address, and so on. So the complete identity of the record. Well, the point is that this zip code, the birth date, and sex, at least at the time where Sweeney made this research, happened to almost completely identify every person in the States. Namely, more precisely, 80% of the population in the States was completely, uniquely identifiable by the zip code, gender, and date of birth. So that means that 87% of the people in this medical database were identifiable and could be, an attacker could figure out whether they have a certain disease or not. So this information here, zip, birth date, and sex, is what is called the quasi-identifier. So in other words, it's a set of attributes that can be linked with the external data, so to uniquely identify an individual. This brought to the idea of the k-anonymity approach, which was designed by Sweeney and by an Italian researcher, Pierangelo Samarati. So the idea is that you should make sure that every record in the database is indistinguishable from at least k-1, k is a number, okay? From at least k-1 other records with respect to the quasi-identifiers. And this can be achieved by either suppressions of the attribute, or generalization of the attributes, or addition of dummy records. And in this way, when you see a set of quasi-identifiers that have been sanitized in this way, you cannot, well, there is always a group of at least K people which corresponds to these quasi-identifiers. So for instance, here is an example of 4 anonymity, so K is equal to 4. The first database in figure 1 is non-sanitized and contains records about people who have certain diseases. There is a part of the database which is non-sensitive and contains the zip code, age, nationality, and is in fact the quasi-identifiers. And the part which is sensitive. So we want to make sure that we sanitize the database in such a way that for every possible quasi-identifier, there are at least four records that correspond to those quasi-identifiers. So we could, for instance, generalize the zip code. So we remove the last 2 digits. We could generalize the age. So instead of reporting the exact age, we just say the group of age, younger than 30 or between 30 and 40 or older than 40. And we remove the nationality. And now you can see that in the second database that has been sanitized, every possible value of the quasi-identifier corresponds to at least 4 records. However, this doesn't, I mean, is something, but is not a complete protection. In fact, more recently, this idea of the K anonymity was developed about 13, 14 years ago. More recently, there have been a lot of attacks showing that even if the database has been K anonymized, still is vulnerable to attacks. The most famous of these attacks, some of the most famous attacks are those by Narayanan and Smatikov. The first one was based on the combination of information from the database of the Netflix price. So this was a database that contained the movie ratings of 500,000 subscribers on Netflix. And they combined this information with another database, namely the Internet Movie Database, and they showed that by knowing just a little bit about an individual subscriber, you could completely identify the record on Netflix. So the idea in general, well, the idea of this attack in general is based on the fact that even if you have a K anonymized the Netflix database, there is always some, you cannot completely, you can never know what the adversary, what kind of background information the adversary might have. And therefore, the idea of generalizing the quasi-identifiers cannot work in all situations. And the second attack is even more interesting. This was based on, well, it was attack on social networks. They considered the 2 social networks, Twitter and Flickr, and they were able to re-identify in the anonymous Twitter graph about 1/3 of the people registered there, with only a 12% error rate, 12% positive false positives. And this attack is completely cannot be defended with the K anonymity at all, because it's based simply on the network topology, so on the relation that the people have with each other. So the K anonymity is completely hopeless here. Now, Let me explain in more, go a little bit more technical detail, well, still high level, but give a bit more technical idea why it's so difficult to protect the privacy. So I'm going to speak about the particular case of statistical databases, which is the field where the idea of differential privacy came from. So the idea is that, the problem is that we want to use statistical databases to get the statistical information. And at the same time, we want to protect the privacy of the participants in the database. For instance, medical databases are often used for statistical research. Typically, we are interested, for instance, in studying the correlation between a certain disease and the age, the weight, the sex, and so on. And of course, people are not very happy if you reveal their state of, with respect to diseases and so on. So, in general, the people are asked that their privacy is protected. So, of course, the people who participate in the database will be reassured that nobody will ever ask queries about, as this particular guy, does he have the disease? Okay, but anyway, these databases must be used for something, and the purpose they are used for is to retrieve aggregate information. So typically we want to allow questions like, queries like what is the percentage of people affected by the disease which is more than 60. Okay, so we are, for instance, interested in studying the correlation between the disease and the age. Now, the problem is that even if you forbid queries about the single individual, still, the queries, the aggregate queries might leak information about the single individual. And let me show an example. It's a bit of a contrived example, but it's the simplest one that makes sense, and you can imagine more realistic examples. But so suppose that the query is, what is the youngest age of a person with the disease in this database? And the answer here in this particular case will be 40. Now the problem is that the adversary might know that there is only one person in the database that is 40, and this Don. Okay, so an adversary that knows some particular background information might completely destroy the privacy of Don by using aggregated queries. Now, k-anonymity, which has been applied a lot to medical databases in the past, would try to solve the problem by saying, okay, no worry, we are going to add, for instance, a dummy record, Carl, that is also of age 40. So at that point, the fact that the answer is 40 will not allow to reveal that Don, will not allow to infer that Don has the disease, because it could be Carl who has the disease, right? Now, what's the problem? The problem is that this solution is not robust under composition, because suppose that the adversary has also access to another database that is there to study the correlation between the disease and the weight, for instance. And now, again, let's assume that this is protected by two anonymity, so for every possible answer to what is the minimal weight of a person with the disease, there are at least two records with the same, that could correspond to that answer, right? 60, there are two people, 90, there are two people, 100, there are two people. Okay, so in this particular case, the answer will be 100. So apparently it's a disease that is induced by being overweight. Okay, so there could be two people, Don and Frank, that could correspond to this, would correspond to this answer. But now the problem is that if the adversary combines the two queries, and combines the two answers, he gets the pair 40 and 100, and there is only one person in the two databases that has this combination, right? So the intersection between the two sets is a singleton. So the privacy is again completely destroyed just by combining two sets. In fact, K-anonymity is particularly vulnerable to, like all deterministic methods, is particularly vulnerable to combination attacks because the intersection of two sets can be a singleton, just for this simple reason. So what is the more recent approach that called, well, I mean, it has been recognized that all deterministic methods have this problem, so people have started thinking to probabilistic, randomized solutions. The idea is to add some controlled noise to the answer so that every answer could be given by several individuals in the database, and preferably by all individuals in the database. So, for instance, we could add noise in this way. We could, to the answer, to the query minimal age of the person with the disease, we could answer, in this case, 40 with the probability half, and 30 with the probability 1/4, and 50 with the probability 1/4. So the probability distribution of getting the answer would be distributed on all the people in the database. And now look at what happens. If you do the same thing on the second database, okay, again, you will have a peak of probability on Don and Frank, that are the real, those which correspond to the real answer, but a little bit of probability everywhere else. So when you make the intersection, when you make the combination of the two answers, you will have a peak of probability on the real guy, which is Don, but you don't rule out any individual in the database. So you can never point the finger and say, aha, that's the guy, right? Because it could be any other person in the database, even with less probability. And this is exactly the idea that is behind the noisy mechanisms that are at the core of differential privacy. So the idea is that instead of giving the exact answer, we give some noisy answer according to some controlled probability distribution of the noise. And of course we have to choose this noise carefully, because if we add the noise indiscriminately, we might destroy the utility of the database. I mean, if we give an answer whatsoever, then we don't get any interesting result, right, from our queries. So there should be a trade-off between privacy and utility, and a good mechanism should try to maximize the trade-off. But in order to speak even about the trade-off, we need to make this definition a bit more formal. So the formal definition of differential privacy is written there. So differential privacy essentially is a framework which comes with the precise definition of the level of privacy and the mechanisms to implement it. I mean, and the methods to implement the mechanisms which satisfy this definition. So the definition is the following: we say that the mechanism K. So K is essentially the answer of the query with some noise. So the mechanism K provides epsilon differential privacy, where epsilon is a parameter, it's a number between 0 and infinity. If for every database X and X prime, which differ for at most one record, we have that the probability to, and for every possible answer in the domain of the answers to the query, the probability that we get the answer Z, if the database is one of the two, say X, differ from the conditional probability when the database is the other one. So the ratio between these two probabilities is bounded by e at the power of epsilon. Okay, so this means that the two probabilities don't differ too much from each other. And this definition, has been defined in this way because it's easier to develop a theory based on this definition, but it's completely equivalent to what I've written here, which is a more intuitively, which has a better intuition as a definition of privacy. So the definition, the equivalent definition is that a mechanism is differentially private, epsilon differentially private, if knowing the answer to the query, well, the answer that is given by K, does not change significantly the knowledge about X for the adversary. So the prior knowledge before knowing the answer and the posterior knowledge about the possible value of X are very close to each other. So namely their ratio differ only for at most e at the power of epsilon. And the nice thing about this definition, if you look at it, we never speak about prior. So this is a definition that completely abstracts from the knowledge of the adversary, which means that if a mechanism is epsilon differentially private for one adversary, it is so for every adversary. So this is nice. And the other important thing, the reason for the success of differential privacy is that it is robust with respect to composition of queries. In fact, we can show that if we combine n queries, which are all epsilon differentially private, then the result is n times epsilon differentially private. So the decrease on the degree of privacy is only linear. It's not catastrophic like in the K. I mean, with the K, anonymity can destroy completely privacy in just combining just two databases. Here, it does decrease, but it decreases nicely. So, implementation. There are various, there are several implementations of differential privacy, but the most natural one is based on the Laplace, is the so-called Laplacian. Essentially consists in adding Laplacian noise, namely negative exponential distribution, symmetric, a distribution like this, which decreases exponentially on the two sides, to the real answer. So the real answer corresponds to the point where there is the peak, and then the possibility to get, the probability to get other answers decreases exponentially with the distance from the real answer. So the formula is this one. This is the distribution of noise. Y is the real answer. Z is the one of the possible values reported by the answer. And epsilon is the privacy parameter. And delta F is the so-called sensitivity of the query. Namely, is the maximum difference that one particular record can induce on the query, on the answer to the query. So in fact it's defined as the maximum between on all possible adjacent databases, so databases that differ only for one record, the maximum difference between of the answers of the query on these two databases. And C is just a normalization factor, which is there to assure that the whole thing is a probability distribution. The idea is that the Laplacian has this particular property that if you take two Laplacians distributed in the same way, namely this and this, with the peak in y1 and y2, the ratio between these two distributions is always the same outside the interval, and it corresponds exactly to a at the power of epsilon. And inside the interval is even less. So this way we are sure that the famous ratio that we have in the definition of differential privacy is satisfied. I mean, the famous bound and the ratio. And some, sorry, how much time do I still have? The clock has disappeared.
10 minutes.
10 minutes, okay, including questions. Okay, I'll try to hurry up. Okay, so here are some implementation, real implementation of differential privacy, and even more interesting are some applications that are already being made of differential privacy. For instance, well, there are several in the field of in the field of medical databases, but also outside that. For instance, the Census Bureau project on the map is using differential privacy, and Google also started the project using which is based on differential privacy. And now, in the 5 minutes that I have left, I would like to show this a generalization of differential privacy, which can be applied to location privacy. So remember, the differential privacy was developed for databases, so it is based on the notion of adjacency between databases. But we can generalize it by using the Hamming distance between databases. You can easily see that instead of speaking about adjacency, you can speak about the property with respect to every pair of database X and X prime, and you put the exponent, the distance, the Hamming distance between the X and X prime. Hamming distance of the two databases is the number of records in which they differ. Now, this brings immediately to the idea of generalizing the definition by replacing the Hamming distance with a generic distance. So X and X prime now they're not necessarily database anymore. They can be elements of any metric space, of any domain that is equipped with the notion of distance. Okay, so the formula, the property remains the same. Just we generalize the exponent to have a generic distance. And now. One can imagine that this distance could be, for instance, the Euclidean distance, and in this case, X and X prime could be, for instance, a location on Earth. So this brings to the possibility of using this framework to provide location privacy, and for instance, for the use with the location-based service. So the idea is that we want to use such a service, for instance, to find a restaurant or any other point of interest, but we don't want to reveal the exact location because we are worried we don't trust the service, or we are worried that it can get hacked or whatsoever. So, for instance, to get the service, fortunately, you don't need to reveal the exact location. Usually, to find a restaurant or to know whether it's going to rain, you don't need to give the exact point. You just need to give an approximate point. So the idea would be that you can use this. You can use a mechanism that implements this generalization of differential privacy. And the idea is that when you generate, when you are in a location, whether you are in a location X or X prime, you would generate an approximate location Z with and the ratio between the two conditional probabilities would be bound by the power of epsilon times the distance between x and x prime. And such a mechanism, for instance, could be implemented by using a planar Laplacian, so the extension of the idea of the linear Laplacian. We only have to make sure that, well, of course we can, one easy way, a very economic way to generate it is by using polar coordinates, but of course you don't want to report the point where the center is the exact location. But of course you don't want to report the coordinates of the point using polar coordinates, because you would then you would reveal immediately the real location, which is because it's the center of your coordinates. So you need to translate this to a universal coordinate system, for instance the Euclidean one. But when you do that, you have to make some approximation. But anyway, to make a long story short, the only we lose a bit on the privacy degree, but this what we lose is practically negligible when you have a double precision. So if your smartphone has a double precision, that will not be a problem. We have so this is something we have developed in my team, and we have made an evaluation of the trade-off between privacy and utility that we get with this method with respect to other methods that have been proposed in the past. In particular, the optimal mechanism by Schrocki and his colleagues, which is a rather famous method, and the simplest method that is I mean, the cloaking method, which was the simplest one that one can imagine, which consists essentially of reporting the zone in which you are instead of the point. For instance, if you are Saint Michel, you report that you are in the Quartier Latin. But this is fixed, in contrast to our method where you always generate a point randomly. I should say that the optimal mechanism by Schrocki et al. Is generated by using, it's a mechanism, so so it like the other one, it reports a different point than the one in which you are, with a certain probability distribution. And these probability distributions are generated, well, it's a discrete probability distribution, and they are generated using linear programming techniques, assuming that you know that the prior of the adversary. So it's a method specific to the adversary, in contrast to ours, which is general. So we have evaluated the three methods, ours and the method of Schrocki, the optimal method, and the method still of Schrocki, generalized, I mean, made the universal by simply assuming that, by simply generating it on the uniform distribution, and the method of cloaking. And the results, well, we have given, we have used the very a generally acceptable notion of utility and privacy, and we have considered these various priors, and the result are quite. We are quite happy with the result, because it turns out that our mechanism is the best one after the optimal one of Schrocki et al. So our mechanism is this. The dark blue one is the mechanism of Schrocki et al. So ours is only outperformed by that. But however, ours is general, is universal, whereas the one of the optimal mechanism is tailored to the specific adversary. Okay, and just very quickly, we have also developed an application based on this. This was mainly to check how interested the people are in location privacy. And we were quite surprised of the result, because we published this software about 1 year ago. We didn't make any publicity, and it has already 60,000 active users. These are the active users. I mean, the people who have downloaded are many, many more. What this does essentially, well, essentially, if you are in this blue dot here, and you are interested in retrieving the point of interest in this area, for instance, the mechanism will generate a random point using the planar Laplacian, for instance here, and then your device will send the black location to the service, and ask, of course, a larger to retrieve a point of interest in a larger area, because you are, of course, you also want to make sure that the area in which you are really interested is covered, right? And okay, so once you get the point of interest, your device will filter out those in which you are really interested. Okay, so this concludes my talk. Thank you very much. I hope